So today we are going to be covering section 5.5 day 2, which is all about what are called differentials. A differential is kind of like a derivative that has just been rearranged. Here's how we came up with a differential. We have two different notations that both mean derivative. dy over dx means derivative, and y prime also means derivative. The reason I'm able to put an equal sign in between there is because they mean the same thing. Basically, what a differential does is it says, get the dy by itself. So in order to do that, I'm going to multiply by dx on both sides, and I get that dy is y prime times dx. This is the formula for calculating a differential. Now, another way that this is sometimes written is like this. df over dx is equal to f prime of x. So if I multiply by the dx again, I get df is f prime times dx. Basically, a differential is describing how much the slope of the tangent line changes in relation to a change in the value of x. So the first thing we're going to do before we try to really get involved here is just practice this habit of calculating these things. So then we're going to get into some kind of involved word problems kind of stuff. Find the differential, which sounds a lot like derivative, sounds like a differentiable, but it's just differentiable, dy, and then evaluate dy for the given values of x and dx. So in order to find dy, we need to find the derivative. So we know that dy over dx for this function would be 5x to the fourth plus 37. In order to make this the differential, I'm just going to multiply by the dx to move it to the other side. You're always going to be multiplying by dx. Now from there, it tells me x is 1, dx is 0.01. So we're going to plug in those numbers. Now, 1 to the fourth is just 1. 5 plus 37 is 42, times 0.01 would be 0.42. Okay, let's do it again. For number 2, first we would calculate the derivative, which would be cosine of 3x times 3, because we would need to do chain rule in this problem, which means ultimately it would be 3 cosine of 3x. Next, we would multiply by the dx in order to get the dy by itself. Finally, it says let's let x be pi and let's let dx be negative 0.02. So if I plug those in, let's see here, cosine of 3 pi. So cosine is the x value, 1 pi, 2 pi, 3, be negative 1. Two negatives make a positive, so 0.06. Another notation that means find the differential would be to just have a d here. Normally when I say find the derivative, it says d divided by dx. If it just says the d and there's no dx on the bottom, that means it must have moved to the other side. That's kind of your clue to swing it over. So the derivative here would be that dy over dx would be the derivative of tangent, which is secant squared of 2x times the chain rule of 2, which is really 2 secant squared of 2x, multiply by the dx in order to get the dy by itself, and we would have 2 secant squared of 2x times dx, and we're done. It doesn't give us any numbers to plug in. That's just the end of it. This function is called the differential. It's kind of like the derivative, it's just the dx is on the other side. Let's do it again. So dy over dx. In order to do this derivative, I would have to do low d high minus high d low, and low squared goes down below. So x plus 1 times 1 minus x times d high would be 1, and low squared goes down below, x plus 1 squared. If I simplify that, this x and this minus x are going to cancel, so I just get 1 over x plus 1 squared, and if I multiply by the dx, I get this. Now sometimes, and I just want to warn you, they're going to put the dx on the top. This means the same thing. Okay, so that would be your answer. Now, like I said, this is just the mechanics of it. Find the derivative, multiply. Find the derivative, multiply by the dx. Find the derivative, multiply by the dx. Sometimes you plug in numbers, sometimes you don't. Let's look at some specific examples. We have two different notations that come up very frequently in math and science. One of them is dy and one of them is delta y. D and delta are just the same letters. One of them is the Arabic alphabet, one of them is the Greek alphabet. So they're kind of similar. When I'm talking about dy, I'm describing the value dy describes the change in the value along the tangent line. When x changes by an amount that we call dx. Now this is really important because dx could also be called delta x, but dy cannot be called delta y. All right, now to find dy, we have to take the derivative and multiply by the dx on the other side. Okay, here's how you're going to remember this. Dy is a derivative. Tangent lines use derivatives. They go together. So if I've got this x value that I'm starting with, and I slide over by some amount, dx means the change in x. So maybe I take 2 steps to the right. Then if I follow the tangent line to that corresponding y value, then the distance between these two y values would be called dy. The distance between this point and this point, which are both part of the tangent line, where the x's are dx's spaces apart. So dx is the distance between the x values, dy is the distance between the y values when you choose 2 points on the tangent line. Now delta y describes the change in the value along the actual function. So we're not going to follow the tangent line anymore, we're going to follow the actual graph. To calculate delta y, you just do y2 minus y1. And x is going to change by delta x, which could also be called dx. They're kind of interchangeable, whereas the dy and the delta y are not. So remember, same situation. X is sliding over a certain number of spaces. Maybe it's sliding over 1 space or 2 spaces. The corresponding values, the points, are going to be on the actual curve now, not on the tangent line. The only difference is where that point is located. This one's on the tangent line, this one's on the curve. If I look at those y values, delta y would be the distance between those y values. So dy is the change in the y values on the tangent line, because derivatives are tangents. And delta y is the change on the actual function because y values are on the actual graph. So how do you calculate these things? Let's let y be the square root of x. Find both dy and delta y when x is 4, and dx and delta x are both 3. Let's start with dy because that's first. to find dy we need to find the derivative. So I'm going to think about square root of x as being x to the 1/2. I'm going to have 1/2 x to the negative 1/2, which is 1 over 2 times the square root of x, which means dy would be 1 over 2 times the square root of x times dx. So to calculate that number, I would just plug in those values I was given in the example. So 4 would get plugged in, and 3 would get plugged in, which means my estimation is that dy would be, the square root of 4 is 2, 2 times 2 is 4, 3/4. Now secondarily, let's calculate delta y. Now remember, delta y is the second thing I'm asked for, which is just y2 minus y1. Now before I can calculate the y values, I need to know the x values. The first x value is going to be 4. The second x value is going to be this number plus this number. I'm starting at the 4, I'm adding 3 because that's delta x. That's how much I'm changing by. So to figure out my y values, I'm going to take these x values and plug them into the original problem. So delta y would be the square root of 7 minus the square root of 4. And I'm going to need a calculator for this part. So the square root of 7 minus the square root of 4, which would be 0.65. Now here's what this means. It means if I use the tangent line to make my estimation, my y values are going to change by approximately 3/4 of a number, which is 0.75. If I use the actual function, which I needed a calculator for, because the square root of 7 was not an easy number, my y values only changed by 0.65. So if I calculate my estimation this way, I'm going to be off by being a little bit big, because this number is a little bit bigger than this number. Now, why is this important? Well, just like with linear approximations, we were able to estimate values using a tangent line. This is telling us how accurate our estimations are. This is telling us that if we use the tangent line, we're going to add 3/4 to our value. This is telling us if we use the actual thing, if we had a calculator, we would only be adding 0.65. So we're going to be off by about 1/10 of a point. Let's try another one. So if y is 1 over x, we're going to find dy, which means we need to take the derivative. I'm going to think about that as being x to the negative 1. So I would get negative x to the negative 2, which would be negative 1 over x squared. Now that means that dy, you can't see what I'm writing, let's try this again, negative 1 over x squared, which means that dy would be negative 1 over x squared times dx. So if I plug in my numbers, I get negative 1 over, the number x that I'm plugging in is 2, times 1. So I would get negative 1/4. Now if I want to find delta y, I need y2 minus y1, which means I need x1 and x2. My x1 is the number I'm given. My x2 is this number plus this number, which is 3. So delta y would be 1/3 minus 1/2. I'm just plugging these numbers into the original problem. Now to figure that out, I would need to make a common denominator of 6. To get to 6, 3 would have to be multiplied by 2, and 2 would have to be multiplied by 3. So I would get negative 1/6. Again, these numbers are a little bit different. If I estimate it using the tangent line, I'm going to have a slightly different answer than the actual y value on the curve, but they're not significantly different. They're only off by a little bit. So tangent lines are good estimators. The last time that these kinds of problems come up is in word problems. So it says here, the radius of a circle increases from 10 to 10.1 meters. Use dA to estimate the increase in the circle's area A. Compare this estimate with the true change and find the approximation error. Let's start by finding dA. dA is a way of writing the derivative of the area formula. So we're going to need an area formula. The area of a circle is pi r squared, which means the derivative of A, and the variable here is r, so dA dr, because that's the variable in the formula, would be 2 pi r. Now, it said I wanted just dA. That's my clue. I should multiply by dr. Now, it says here, I'm starting with a 10 meter radius. I have a 10.1 meter radius, which means x, or my original r, would be 10, and dr would be 0.1, because my radius got 0.1 meters bigger. So dA would be 2 pi times 10 times 0.1, which would be 1/10 of 10, which would just be 2 pi. And since I'm measuring the area, I want to use units here. Area would be meters squared. So I am estimating that my change in my area, dA, of my circle would be about 2 pi, which is about 6.28. Now, if my estimate is that I'm going to get about 6.28 meters squared larger, let's calculate how much larger I actually get and see what happens. So delta A would be my original, R1 would be 10, R2 would be 10.1. That's what they told us me in the directions, is that my first radius was 10, my second radius was 10.1. So to calculate my change in my area, I would just do my area at radius 2, minus my area at radius 1, my change in my area. So I would get pi times 10.1 squared minus pi times 10 squared, which, if I use my calculator, I get 10.1 squared is 102.01 pi minus 10 squared is 100 pi, so I get 2.01 pi, which is pretty close to 2 pi. Those are pretty accurate. So my accuracy, or my approximation error, would just be, how far off am I? Well, my actual number was 2.01 pi minus 2 pi would be 0.01 pi meters squared. So how accurate was I? Pretty good. 0.01 pi would be a pretty small number. So there are 3 parts to this answer. Did you find dA? Did you find delta A? Did you find the approximation error? Let's do another one. Suppose the Earth were a perfect sphere. We determined the radius was going to be this number, plus or minus 0.1 miles. What effect would the tolerance of plus or minus 0.1 miles have on our estimate of the Earth's surface area? So, surface area of a sphere is 4 pi r squared, which means, and I'm just going to call this S for the purposes of our experiment here, if we want to estimate the error, we would have ds over dr equals 8 pi r. If I multiply by the dr, I get 8 pi r dr, rdr. Now it's telling me my radius, and it's telling me my estimation error. So ds would be 8 pi times 3959 times plus or minus 0.1, which, I'm going to use my calculator for this, 8 times 3959 times 0.1, 3167.2. And we're doing surface area, so miles squared. So, pi. Ooh, I almost forgot the pi. Now, that means that changing the radius of the Earth by a very small amount, 0.1 miles, has a significant impact on the surface area by 3,167.2 pi miles, which, if you actually multiply that together, is 9,950.052 square miles of the Earth's surface that changes. That's the size of some countries. Like, that's crazy. Now, what would the actual, or it doesn't say, it just says what effect would the tolerance have on our estimate. It means we could be off in our estimate by 9,950 square miles. All right, that's the end of our lesson. We're basically just saying take a derivative, multiply by the d whatever to the other side, plug in some numbers, and then that gives you an estimate of how good your estimate is. Or not an estimate of how good. It tells you how good your estimate is. So if you use a tangent line to estimate a value, how far off could your estimate be based on how far away you are from the point at which you were writing that tangent line? All right, I will see you guys tomorrow. Have a wonderful afternoon.